In this video, we're going to discuss power functions and polynomial functions. This information is taken from the free online textbook from openstacks.org. It's the college algebra book, and it comes from the section 5.2. So these gray boxes come directly from that textbook. You can access this free textbook through openstacks.org, and I have a link throughout the presentation so you can see it. If you want to pause the video and go to the website and look for more information, that would be great. So the first thing is the power function. A power function is a function that can be represented in the form f of x equals k times x to the p, where k and p are real numbers and k is known as the coefficient. So the number in front is called the coefficient. So an example of this might look like f of x equals 3x to the fourth. So notice the x is the variable and the k and p are numbers, right? So they're 3 and 4 in this case, but those are the numbers, the x is the variable. A polynomial function looks like this f of x. N is a non-negative integer, so that's important. It's a non-negative integer, so it can be 0 or a positive number. A polynomial function is a function that can be written in the form of f of x. This is called the general form of a polynomial function. Each a sub I is a coefficient, so that's the number in front, and it can be any real number, but a sub n cannot be 0. Each expression is a term of a polynomial function. So let me give you an example. So this might look like, f of x equals, and you've seen polynomial functions before, 4x cubed minus 3x squared plus 2x minus 8. That's an example of a polynomial function. So you can see that all of the exponents are non-negative integers. The first one is the biggest. It's in descending order, and I'm talking about the exponent. So the first exponent is the largest. It's in descending order, so this would understood to be a 1. This is a general form of a polynomial function. You can see the a sub i's. So all these a sub i's are the numbers in front. Those are the coefficients. The last one is called a constant. And you can see the terms are separated by plus and minus signs. So this 4x cubed is a term. Negative 3x squared is a term. 2x is a term, and negative 8 is a term. So this has 4 terms. Okay, so polynomial functions, power functions. Notice that the power function is like one term of a polynomial function. So if you only have one term, a monomial, that could be considered a power function as long as it meets the criteria of having k and p be real numbers. Okay, so let's see what we're going to do with that information. So we want to identify the function as a power function, a polynomial function, both a power function and a polynomial function, or neither. So in this first example, we have x squared cubed. So realize that we can rewrite this as x to the 6th. So this is an example where you multiply the exponents. X to the 6th. So notice I have one term. So this is definitely a power function, but it's also a polynomial function. So it's both a power function and a polynomial function. So it meets the criteria for both. Number 2, we have an f of x equals this whole thing, right? So what we need to do is we need to have an idea of what this is going to look like. So you could multiply it all out, distribute everything, get it all multiplied out. But hopefully you have an idea in your head of what this will look like. So first of all, you can tell from looking at this, it's not going to be one term. So it's not going to be a power function. So the choice is it's either going to be a polynomial function or it's going to be neither. So if we multiply it all out, it is going to look like a polynomial function. Notice the variables are not in the exponents. We're going to have positive exponents, non-negative for sure. So this is going to be a polynomial function. If we look at number 3, at first you might be tempted to say that this is a power function because it has the one term. But notice where the variable is. In a power function, the variable is the base, and then you have an exponent that's a number. In number 3, you have the number as a base, and the variable is in the exponent. So this is neither. So if you have the variable and the exponent, that is not a power function or a polynomial function. It's neither. Okay, so a couple more things to talk about. We talked about terms. So the leading term is the term that has the highest degree, which means the highest exponent. So the degree is the exponent on the variable. So for example, x cubed, the degree would be 3. We talked about the coefficient. The leading coefficient is the coefficient that's in front of the leading term. So let me show you a quick example. Let's say I had, f of x equals 5x cubed minus 2x plus 8. So first of all, we're going to see that this is in descending order. That means the variable's exponents go down as you go to the right. So if we look, we have an x cubed, so that exponent is a 3. We have an x. There's no exponent written there, but it's understood to be a 1. And then we have no variable at all on the constant. So that exponent, so this technically is x to the, let me put it in a different color. So the red stuff I'm adding, it wasn't there originally. That is an x to the 0 power, because remember, anything to the 0 is 1. So we have our exponents going down as we go to the right. So 3, 1, 0. The leading term does not necessarily mean the term that's first. It means the term associated with the highest exponent. So this, it is first here because they're in descending order, is the leading term. So the degree of this polynomial would be 3. The coefficient, the leading coefficient, would be 5. So we're going to be looking for those on the next few examples. The leading term is very important. It's important that you should be able to pick this out because it's going to tell you some stuff about the end behavior of the graph. So it's going to tell you an important part of graphing when you're trying to graph these. So the leading term, first we're going to identify the leading term. Remember that that is the one with the highest exponent on the variable. So for number 4, we have a 7 and we have a negative 2x squared. So the negative 2x squared is going to be our leading term. Even though it's not first, that is the highest exponent. So that's our leading term. The degree is the exponent. So the degree is 2. The leading coefficient is negative 2. All right, number 5. In order to find this, you're probably going to need to distribute it all the way out. So I'm going to go ahead and do that here. If you can do it without it, like if you can mentally do it, that's fine. What you would do if you wanted to do it mentally is simply multiply all of the highest degree terms from each factor, and that would give you your leading term. But I'm going to go ahead and multiply it all out. So we're going to have x times 4 is 4x, and x times negative x squared will be negative x cubed. Then I'm going to bring down the next term, or the next factor, and I'm going to distribute there again. So I'm going to have 8x squared plus 4x minus 2x to the fourth minus x cubed. So now I'm going to look for the leading term. Remember, the leading term is the one with the highest exponent. The highest exponent I see is a 4. So here is my leading term. My degree is 4. And my coefficient, my leading coefficient, is negative 2 again. So again, you're looking for the highest exponent. That's your leading term. So here is a chart that shows you the end behavior of graphs depending on their leading term. So if you have an even power, so this is the exponent, so this is the exponent, and this is about the leading coefficient. Okay, so if your exponent is even and the leading coefficient is positive, so k is greater than 0 means positive. Here k is less than 0 means negative. Then if it's positive and it's an even power, your ends are going to go up. So the example of this is x squared. This is a positive x squared. So this is positive, right? And this is even. 2 is even. So the ends of your graph are going to go up. And we know that because an x squared is a parabola, and that's exactly what shape that is. So the ends of your graph are going to both be facing up. Let's look down now. When do I have both my ends going down? The example that we should be familiar with is negative x squared. So notice here I have a negative and I have an even. So anytime you have a negative coefficient, the leading coefficient is negative, and your degree is even, your ends of your graph are going to both be facing down. Okay, so now let's look at the odd power. The positive odd power, the example we should be familiar with is x cubed. So here, this is a positive, and this is an odd. So notice that an x cubed is exactly the shape it shows. The left-hand side is going down, the right-hand side is going up. That would be the end behavior for a positive odd. And then last, we have negative x cubed. Remember, that reflects over the x-axis or the y-axis. So this is a negative, and it's an odd. Notice here your end behavior, the left side is now going up, and the right side is going down. We're going to be showing these again multiple times, but this is the end behavior that we're going to be looking at, and it's determined by the sign and the exponent on the leading coefficient, or leading term. Okay, so intercepts and turning points of a polynomial function. A turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. Let me stop right there and do a quick example. If I have a graph that looks like this, and you want to look for turning points, a turning point happens here because it goes from increasing to decreasing. It's going up It's going up until I get here, and then it starts to go down. It's decreasing. So this is a turning point. This is another turning point. Here is a turning point, and here is a turning point. So the number of turning points is, well, let me say this. The degree, if the degree is n, then there are at most n minus 1 turning points. Okay, so in this example, I have 4 turning points. That means the degree, the least possible degree, is the 5th power. So that's the smallest possible degree it could have. It cannot be an x to the 4th, x cubed, x squared, x to the 1st. It cannot be those. It has to be at least an x to the 5th. It could be greater than that, like an x to the 6th or 7th, just based on turning points. Okay. So turning points tells you some information about the degree of the polynomial. Then we have some information about the y-intercept and the x-intercepts. Okay, so let's look at some of this information now with examples. So determine the end behavior of the function. So we just want to know what's happening at the ends of the graph. You do that by looking at the leading term. So in number 6, we only have one term, so that has to be the leading term. We want to look at the leading coefficient. It's positive. And we want to look at the exponent. It's even. Remember, a positive even, the end behavior looks like that. So on the left-hand side, as x goes to negative infinity, y goes to infinity. So what that's saying is, as x goes to negative infinity, so for the domain, we're going to the left this way, but we're going up. So left is negative infinity, up is positive infinity. So that's what we're getting there. For the other direction, as x goes to infinity, so this means as we're going right in the x direction, we're also going up. So y goes to infinity. So as x goes to the left, so this means as x, I can't spell goes. As x goes left, y goes up. As x goes right, y goes up. So for the y, a positive infinity indicates up. For the x, a negative infinity would indicate left, and a positive infinity would indicate right. So remember, x is left and right, y is up and down. So that's kind of what we're looking at. Let's look at the next one at number 7. So number 7, first we want to find the leading term. So we're going to look at all the exponents. The biggest exponent I see is the 6. So this negative 3x to the 6 would be the leading term. So now from there I can pick out the degree and the leading coefficient sign. So we have a negative and we have an even exponent. So a negative even goes down, right? Remember, that's like a negative x squared. It flips it upside down. So now we want to talk about as x goes, let me make sure I separate here. Okay, so as x goes to negative infinity, so you always start by looking to the left. So as we go left, we also go, how does the y go? It goes down. So y goes to negative infinity as well. So as x goes left, y goes down. Now we want to talk about as x going right. As x goes right, which means positive infinity, y also goes down. So y goes to negative infinity. Okay? Number 8. Here, in order to find the leading term, we need to distribute this out. So we will get 2x to the 5th minus x cubed plus x squared. Here, the leading term is the exponent of 5 is the largest, so it's the first one here, 2x to the 5th. In this case, I have a positive coefficient and an odd exponent. So a positive odd. Remember, this is like an x cubed. So on the left, it's going down. On the right, it's going up. That's our end of behavior graph. Now I need to describe it in terms of x and y and infinities. So as x goes left, you always start as x goes to negative infinity, which means as x goes left, y goes down, right? As x goes left, y goes down. So as x goes to negative infinity, y goes down, which means it goes to negative infinity. Then you want to talk about x to the right. So as x goes to the right, which means as x goes to infinity, y goes up, which means y goes to infinity. So there is your description of the end behavior. So my advice is to memorize the little charts. Memorize these little graphs and then figure out the x, y, and infinity stuff from those charts. I would not try to memorize all those x's and y's and negative infinity and positive infinity. That's going to seem extremely overwhelming because it's all so similar. If you just remember what they mean and you look at the little chart, then you'll be able to figure those out on your own. All right, so let's look at the next one. Find the intercepts of the function. So this means x and y intercepts. So if it doesn't specify, you should find them all and make sure you label your answers. Label the x-intercepts and label the y-intercepts, okay? So first we're going to find the x-intercepts. Remember, x-intercepts are found by letting y be 0. So this will be 2x minus 1, x plus 2, x minus 3 equals 0. This is all factored for us. So now we can set each factor equal to 0 and solve to get our intercepts. So 2 is the first factor. Keep in mind that I can set that equal to 0, but it does not have a variable, so it does not lead to an answer. There's no solution to that. X minus 1 equals 0. If I add 1 to both sides, I'm going to get x equals 1. X plus 2 equals 0. If I subtract, right? If I subtract 2 from both sides, I'll get x equals negative 2. And then x minus 3 equals 0. I'm going to add 3 to both sides, so I get x equals 3. So each of these will give us an x-intercept. So my x-intercepts are 0, 1. Nope, what's wrong with that? I totally did that backwards. I'm really off my game in this video. X-intercept, we've got the x is 1 and the y is 0, right? So you have to make sure you put them in the correct order. So 1, 0, negative 2, 0, and 3, 0. Those are my 3 x-intercepts. Now I need to find my y-intercepts, or intercept, right? So that's going to be when x is 0. So I'm going to have y equals 2 times 0 minus 1 times 0 plus 2 times 0 minus 3. So that's going to be 2 times negative 1 times 2 times negative 3. So 2 negatives will make a positive. 2 times 2 is 4 times 3 is 12. So my y-intercept will be 0, 12. So there are my intercepts for number 9. Okay. Now I'm going to work on number 10. So same thing, I need to find the intercepts. So to find the x-intercepts, I'm going to let y be 0. So that means x to the 4th minus 16 equals 0. Well, this one is not factored for us. So I have to do the factoring in order to find the intercepts. So I can break this down. This is a difference of squares. So x to the 4th will break down into x squared and x squared. And then 16 will be 4 and 4, 1 plus, 1 minus. Now I'm going to try to factor those again. Remember that the sum of squares does not factor, so that has to stay as is. And then x squared minus 4 will factor into x plus 2, x minus 2. And now I'm going to set each factor equal to 0 and solve. So x squared plus 4 equals 0. If I try to solve that, I'm going to subtract 4 from both sides. That's going to give me x squared equals negative 4. Then I have to take the square root of both sides, putting in a plus or minus. I'm going to get x equals plus or minus 2i. We are finding x-intercepts on the real number plane. So these are not going to lead to x-intercepts. So if you get imaginary numbers, these are not going to be valid solutions. So you can ignore those. Those are not intercepts. So I shouldn't say solutions, they're just not intercepts. So now we have to do the next part. We have x plus 2 equals 0. We're going to subtract 2 from both sides. So we get x equals negative 2. That will be an intercept. Then we have x minus 2 equals 0. Here we're going to add 2 to both sides. So we get x equals 2. That will be an intercept. So in this case, we have 2 x-intercepts. And they are negative 2, 0, and 2, 0. Okay, so now we need to find the y-intercept. So the y-intercept is when x is 0. So y equals 0 to the 4th minus 16. Well, that's just going to be negative 16. So the y-intercept is 0, negative 16. All right, so there's that one. That one's done. Okay, so let's look at number 11. So if I want to find the x-intercepts, whoa, how come I did equal 0? So this originally, right, should not say equal 0. Let's make it be in function notation here. G of x is equal to x cubed minus 8. Okay, so now let's try that again. We're going to have, to find the x-intercepts, we let y be 0. Now it'll look like that. X cubed minus 8 equals 0. So I want to try to factor this. So we're going to have x minus 2. This will be x squared plus 2x plus 4 equals 0. So that is a difference of cubes. If you do not know how to factor that, you need to go back and watch the video on factoring. So that is how you factor the difference of cubes. Now you want to set each factor equal to 0 and solve. So x minus 2 equals 0. Add 2 to both sides. You get x equals 2. So that is one intercept. And then the other one is x squared plus 2x plus 4 equals 0. That is not going to be factorable. Whenever you do a difference or sum of cubes, the trinomial part, the second factor, is not factorable. So if we want to try to find that, we can use the quadratic formula. So that'll be x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And so when we simplify that, we will have negative 2 plus or minus the square root of 4 minus 16 all over 2. That's going to be negative 2 plus or minus the square root of negative 12 over 2. Right here, this is our big red warning sign here, the negative under the radical. This is going to give us imaginary, right, the I, the complex numbers. This will not lead to x-intercepts. So these are going to be excluded. So the only x-intercept we get is the x equals 2. So the only x-intercept we have in this case is 2, 0. Okay, and now we're going to have the y-intercept. That's when we let x be 0. So we will have y equals 0 cubed minus 8. That's just going to be negative 8. So the y-intercept is 0, negative 8. All right, so that should give you some examples to look at for finding the x and y intercepts in several different scenarios. Okay, so let's see what we have next. So graphs of polynomial functions. So when you're looking at a graph, in order to tell kind of the telltale signs of a polynomial function is number one, they are smooth curves. So they do not have sharp corners. Number two, they are continuous. So we have no breaks in the graph. So let me show you what an example would be of something that doesn't meet these criteria. So for the first one, a smooth curve. Remember from our toolkit functions, we had the absolute value function. That's a v. That is not a smooth curve. It's a sharp corner right here. So this would not be a polynomial function. Okay. Something that's similar, right, would be a parabola. See how that's smooth at the end? This is a polynomial function. Okay? Something that has no breaks in the graph. So let's say I have something that looks like this, and then it picks up here and continues. That is not a polynomial function because of the big break in the middle. There's a hole. So that would not be a polynomial function. So as long as it's a smooth, continuous graph, then that is probably a polynomial function. For our purposes, it is going to be a polynomial function. Okay, so determine whether the graph of the function provided is a graph of a polynomial function. And let me just tell you one thing here. We haven't gotten to these yet, but you will see some graphs that look like this in your homework, I believe. These are exponential and logarithmic equations. These nice curves like that, or like that, okay? Those will not be polynomial functions. So keep that in the back of your head. Okay, so continuing on. Determine whether the graph of the function provided is a graph of a polynomial function. If it is, then determine the number of turning points and the least possible degree of the function. So number 12, this is a smooth curve. It does not have any breaks in the graph. So I would say yes, this is a polynomial function. So polynomial function. Okay, Okay, so since it is, we need to find the turning points and the least possible degree. So here is a turning point right here. Here's a turning point right here. Remember, the turning points are the local maximum or minimum values, or they're where they change from increasing to decreasing or decreasing to increasing. So we can see that we have 2 turning points. So that means that the least possible degree of the function is a cube. So it would be x cubed, because it's 1 more than the number of turning points. So since there are 2 turning points, this has to be at least an x cubed. And that's all they wanted us to do for that. So number 13, we look at this one. Yes, it looks like a smooth curve. There are no sharp edges. And there are also no breaks. So we're going to say, yes, this is a polynomial function. We're going to look for turning points. So here's one. Here's one. Here's another one. Those are all the turning points that I see. Since there are 3 turning points, this is at least degree 4. So this is an x to the 4th or larger. Okay, number 14. This is the last one, I believe. Yep. Okay, so number 14. Is this a polynomial function? This is actually similar to what I gave an example up top, right? This is not a polynomial function because it has a sharp edge. And furthermore, we know that this is the graph of an absolute value function. And an absolute value function does not meet the criteria for it to be a polynomial function.